Welcome back. So let's resume the last session. The first speaker is Jan. Yes. So the first speaker is Jan, but let's just clear a few very short announcements. Let me just let you know one from Cheryl. Don Uberliving will leave for the airport at 1, and he has space available on his car. So if you want, do join him at the entrance. Is that the? And then back to you.
So immediately after lunch, starting at 2, there will be a meeting in room 3131. That is the 3rd floor. So you'll have to go either upstairs or elevators down at the south end of the building. The topic will be what are the scientific requirements and some technical requirements for NG gong / spring in the world of helioseismology, not the other aspects. So 2-hour meeting to talk about that.
And I would just add that the cafeteria is closing at 1:30.
Oh.
So if you do want to get lunch, I'd get over there at least several more minutes before 1:30 in case there's a line. So hopefully that won't be an issue.
Okay.
Very well. We are ready. Jan, please go ahead.
Okay, thank you. So my idea here is really, I wasn't quite sure what I was going to say, but to set the scene for a discussion that we are having afterwards. I think that's a much more important part of it. Before I start, I should point out that many years ago, we heard about the meeting in 2006 already. At that time, Jesper pointed out that I was moving to the dark side, moving from helioseismology to astroseismology. And so my contemplations are going to be a bit biased towards the stars, even though, of course, this meeting has been very much also about the sun. And the second thing I should point out is that I am, of course, a dinosaur. And so some of the things that I point out would reflect that. But that would be a good start of a discussion, at least. And that's the reason why I'm presenting it that way. So we talked already about why we're doing all this. What's the point of the science that we're doing? And of course, one of the arguments that for what we're doing is, and we use that when we're selling what we're doing, next generation gong or whatever, is that what we're doing is useful in a broader sense. So in the case of the solar physics, I just put that down, space weather. Climate change, of course, is very topical. We now know that this is also important for epidemiology. So it is useful, and that's a very good reason for doing that kind of science. And similarly, we're seeing very much, and this really has caused a rejuvenation of the interest in stellar astrophysics, that we use stellar astrophysics in exoplanet research, galactic archaeology, and of course also studies of the chemical evolution of the universe. And Dan pointed that out, that many of the stars that we are going to observe in the future are being observed not for their own sake, but for the studies of other aspects. But of course, we all also know that the real reason we are here is to understand so simple a thing as a star, as Edison pointed out. And that really is sort of a little bit like fusion. I mean, Edison thought that in a not too distant future we'll understand so simple a thing as a star. We also know that the practical use of fusion is always 50 years in the future. And so maybe in 50 years we'll understand so simple a thing as a star. But that really is what we're trying to do and what we're working on here. Of course, we've also seen in this meeting, and this is no surprise, that there are very many things that we don't understand and that we're working on: convection, how it interacts with rotation, instabilities in mixing, diffusion, radiative acceleration, evolution of rotation, magnetic fields. We don't understand magnetic fields, I certainly don't. dynamo action, and then all the aspects of the physics of the oscillations, which are interesting, and again go back to try to, we need that to carry out the astroseismic analysis that we try to do. So these are really the issues that we have to address and that we're working on improving. And of course, what we see, I have seen in the last few years and continue to see, is that our possibilities for doing that are really exploding. They have been exploding and they continue to do so. In solar physics, we have the SOHO data that we haven't completely, certainly far from completely analyzed and used. We have the SDO, which is still ongoing. We have the GOM data. We have the BISON data. We're looking forward to next generation GOM. So we're going to have an amazing amount of data that should help us improve our understanding of stars. And similarly, in stellar astrophysics, we've heard many times that we are very, very far from making full use of the Kepler data. We should remember that the Kepler data, in some sense, as Yvonne pointed out, are going to be the best data we have for many decades. None of the missions planned are going to have the time duration of the full Kepler data. Even Plato is only going to observe each field for 2 years. We can use tests in that manner. We can try to do that. So, but the Kepler data are far from utilized. We have the test data flowing in. We can supplement that with the data from Gaia, which is really revolutionizing many aspects of stellar astrophysics. We have large surveys of chemical composition of stars, which is also very important for what we're doing. And we have Plato coming up, and then, of course, as Dan also remarked, we have ground-based facilities that supplement all these marvelous possibilities. And then another thing that we also is exploding is our ability to model stars, model hydrodynamical processes, making data analysis in terms of these supercomputers that are available and continue to become more and more powerful. When I give talks about, public talks about stellar evolution, I show a slide that Birte made in 1988, where I was using the Cray 1 computer at NCAR. And of course, that Cray 1 computer is not nearly as powerful as a laptop that I'm presenting this talk on. So that we have a huge amount of possibilities for doing the research that we want to do. And then we've also, this week, heard about new analysis techniques that is also improving our possibilities. We heard about global helioseismic analysis using different combinations of variables which provide different kinds of insight into the solar interior. We heard about local helioseismology and the numerical forward modeling, which is becoming possible because our computers are becoming more powerful. We heard about the mode coupling analysis, I'm sorry about that, that was developed by Martin Woodard and developed further by Marcus Roth and then applied by Shravan, giving some very interesting results about the dynamics of the solar interior. And then, of course, we heard about the astroseismic inverse analysis, which is becoming possible thanks to the quality of the Kepler data. And all this is going to help us improve our knowledge about stellar interiors. And then we also have a very topical issue on the use of artificial, let's call it intelligence. I'm not quite sure whether it is intelligence. I'll get back to that a bit later. But certainly new ways of analyzing data that allow us to, in particular, dealing with the very, very large data sets that we are gathering. So that's all very good. What do we hope to get out of that? Well, yeah, there are also these different ways that we can analyze the data, and I think that's important to keep in mind. And it has sort of been partly apparent in the meeting. We can do very detailed analysis for selected stars. It's clear we can't analyze 1 million stars in detail, but there are stars where the data are so good that it's worthwhile spending a few months trying to analyze those data. And that is what was called boutique modeling. I think at the CASC meeting we had here in Boulder in 2011, very important meeting, and maybe it was Savita who introduced that term. I'm not sure actually, I can't remember it now, but like sort of, you could also call it bespoke analysis. And then the second way of doing this is to do an ensemble analysis and characterize the properties of large groups, well-defined groups of stars. And that, of course, is what we can do because we have the huge amounts of data on the Kepler red giants, the test data, the Gaia data, and so on. And the distinction here really is that for this, we certainly need human intelligence. We need to know what we're doing. We need to really be creative in the way that we interpret the data and combine the different data products that we have for these stars. In this area, that's really where we have to lean on machine learning because the amount of data is so huge that there's no way we can do it manually. Although I forget who it was who talked about looking at data for 30,000 stars, but just sitting on the computer and pressing the next button and looking at the power spectra or whatever. And that's also a way of doing it, but you get tired. There is actually another way of doing that, which was also alluded to, and that is crowdsourcing citizen science and having large group of people looking at the data. And I think that is a very powerful technique that we should probably use more. Because there are very many people out there who are interested in looking at these data and doing this kind of, contributing to this kind of science. And that has really had some very good and important results. So, quite a few of us are Michael's siblings. And so, descendants from Douglas. And one of the things that we learned from Douglas, I think we heard that many times, all of us, is that the object of computing is insight, not numbers. I think we have to keep that in mind, and I think we can extend that a little bit to apply it also to observations. And who cares what a power spectrum looks like? We really want to use it to get into knowing something about the stars. And I would also like to possibly distinguish between insight and understanding. In some sense, what we're doing is really to gain understanding. Understanding is one of these things that's very hard to define. I can't tell you what understanding means. We can discuss that forever. We can take it up in the discussion session. But you sort of know that you understand something. You can sort of feel that you understand something when you do. One way to characterize it is that if you really understand something, you should be able to explain it to your grandchildren or to your grandmother, depending on your age. And so getting to that point is really an important goal of what we are doing. A very difficult goal. We all know the example that, well, sort of implicit in Saskia Hecker's very interesting poster, to understand why stars become red giants. It's obvious that they do, all our models do, the stars are there, so they clearly do. But people have been working for 50 years to try to, in that sense, understand it, in the sense that they could explain it to their grandchildren. Since they've been at it for 50 years, the grandmother is probably no longer there. So that's one thing that Douglas taught us. And the second thing that Douglas taught us is never to carry out a calculation before you know the answer. And that's tough. But of course, the idea there is that if you can always pop equations into a computer and you get something out. But how do you know whether what you get out makes any sense or not? And that's really where having some idea of what to expect helps a lot. And the further extension of that I just want to mention, everything I'm saying here is obvious. So I apologize for that, but I think it's good to have in mind in discussing what we're doing. And that really is the interplay between analytical insights and numerical computations. We had a brilliant example of that in Pascal's talk yesterday, where she did the modeling of the, simplified modeling of the tachocline. I don't know if Pascal is still here, she may not be. But combined that modeling with some very simple approximate analysis of the physical system and related that to the numerical results. And I think that kind of interplay is something that we were also taught by Douglas. It's something that Michael was a master of, and something that's very helpful in combining all these. Of course, the data are there also, and that's really part of the computation, the fitting the data, understanding the results of those fits to the data, and then finally maybe reaching an understanding of the physical processes that we're looking for. So now I get into a dinosaur mode. I apologize for that, but I think I'm allowed to do it. We're seeing, it's nothing completely new, but we're seeing sort of the rise of the black boxes. And that, to me, is a concern. We have program packages that very conveniently take observations, do something that might involve artificial intelligence, and out of that comes stellar parameters, properties of stars. And we don't really, when we use that black box, have very much idea about what's going on inside it. But of course, the numbers come out, we have numbers, that's great, that's what we need. And those numbers we can then use and carry on and fit to stellar models using another black box called MESA, which is a huge program package developed by many, many people. It's wonderful. And out of that comes a stellar model, and then we trust that stellar model. And the danger of all that is that these things are so convenient to use that we use them without thinking too much about what goes on inside the boxes. We frankly have no idea. And therefore also really don't have a very good idea about whether we can trust the results. But of course we can write papers about that, and that's in one sense, the ultimate goal of what we're doing, to have a lot of papers and a lot of public citations. And of course, good way to get citations is to screw really badly up in what we're doing here and produce a model that's obviously crap. And then there are lots of papers pointing out that that's crap, and then you have a lot of citations. So in that sense, the system works. But it's not so clear that we gain understanding by doing this. And so that's one issue that we could discuss that, see whether we can do maybe better. And then there's this term that I came across in a paper by, actually, well, it was a paper by Thiago where he talked about analyzing the data using deep learning. Deep learning, that's a wonderful term, but what do we really mean by it? Do we mean this, or do we mean that? And I think we might want to have a little bit more of that, and maybe, of course, use this, but this is really what deep learning is about. I'm sure you recognize these two guys, a younger version of this guy, Niels Bohr and Einstein. And they had deep learning, and we can't all aspire to reach that level, but we can try to get a little bit towards that. So just really getting back to contemplating the future, and of course all these aspects are part of what we need to think about when we contemplate the future. One aspect that we touched in connection with Marcus's talk is funding. We have all these wonderful things we want to do. We have all this fantastic data that we should use because it's been expensive to create those data. And that all depends on funding. We need funding, of course, to develop even newer and better instruments. And that's part of the SPRING effort and the next generation GONG. We need money for the support of the data analysis of data that we already have, and as I mentioned, we have an amazing amount of data that are still waiting to be analyzed. And that's sort of also related to that, very closely related to that, because we need hands or brains. We need support for PhD students and postdocs. And then very importantly, and that's where it gets really difficult, we need faculty positions, permanent positions at our various research organizations to make sure that we have this continuation of the research that we're doing. And I know mostly about what's happening in Aarhus, and the answer there is very little. Although we have been able to hire 2 new faculty people recently, chances of going beyond that are fairly slim, but I think it's a problem almost everywhere, and one that we somehow have to work with, because without faculty positions leading the research, this research is going to die. And then finally, we need these new brains. And so we need to consider how we train the future generations of scientists. As Stan pointed out, it's been very, very encouraging to see how many young people are entering these fields. Certainly at the CASC meetings and TASC meetings, there have been very many brilliant young scientists coming in. And of course, then we get back to the issue of faculty positions, because we really want to catch the best people in that generation. But we also want to train the new students. And one thing, again, getting into my dinosaur mode, that's very worrying, at least in Denmark, is that when you look at the high school education in mathematics, that is very strongly moving into using computers to do these manipulations. These kids don't know how to use a pen, a pencil, and a piece of paper to do a simple integral when they get to university. That may be just a Danish problem, but my guess is it probably isn't, because these things tend to be more or less global. I was delighted to talk to Lisa yesterday about how she derived her equation that was about this long. And I sort of assumed that this was done by symbolic manipulation. And she claimed that she actually did it by hand. And I was delighted about that. So that's hope. But we need many more Lisas. And so we should really work towards that. And then, sort of to get back to the black boxes, we need to know that they understand what they're doing when they're computing stellar models, computing oscillation frequencies, understand why the models react the way they do when you change parameters. And that also goes back to this relation between analytical insight and numerical calculations. We need similarly to understand that they understand the statistical properties of data when they do the data analysis. What does data significance mean? There's been all this crap about Bayesian ratios and significance of certain results. A classical example is actually HD 49933, where there was a Bayesian analysis showing that the mode identification was definitely A, with a likelihood of 10 to the 14. In the first analysis, it was actually B. So we have to be very careful with this kind of statistical analysis. And of course, we need to understand what's going on. I don't. There need people to help me understand the statistics. And then, of course, we also need to make sure that these young scientists know why they're doing what they're doing and how what they're doing fit into this broader context of science and society and literature and music and all that. To get the broad view of culture, scientific culture, and other aspects of culture. And you could say that what I'm really asking for here is also some aspects of deep learning. And one reason really to pull all this up is that this is very much Michael's way of working, and we want to preserve Michael's spirit in science and life. So thank you very much.
So we move on to the discussion. So after all these provocative statements from Jan, I'm sure we have a lot to discuss. So Rafael Garcia is organizing discussion.
well, anyway. Okay, anyway, I let it like that. Okay, anyway, it's enough. So, can you hear me? Yeah. So, that's nearly the end of the conference, where we will still have one more talk after mine, or mine talk. So, I want to invite to all of you that haven't had the opportunity to talk here, and I'm very happy that I will raise many of the things that Jorn talked in his presentation. So the days that I have write down many points that were raised during these 3 days, intensive days of conference, and I tried to follow a little bit the spirit of Michael. So I started with theory. There will be something about modeling, observations, etc. So my idea here is try to project it all of us in 10 or 20 years time from now, and trying to see how we can solve all of these things. So, for example, in the theory and methods, we know that Michael were very good and funded many, the basis of many new methodologies, inversions in particular. So I've been discussing with Sarvani and Rachel, so they are there still. So I wanted to go beyond Mike's methodologies, and then I wanted to ask Rachel about the future of inversions, and she was saying, yeah, 2D models, 2D inversions, but maybe 3D inversions, including time. So what do you mean by that? What should be the next big step that we have to make in these methodologies to go further?
Okay, maybe this is a crazy idea. I wouldn't begin to know how to implement it. But when we do inversions, particularly when we do regularized inversions, we're penalizing jumps in space. We want things to be smooth and continuous. And it did occur to me to wonder whether we could we have whole series of sets of data, whether we could analyze them and actually put in a penalty term for jumps in time so that you get a smooth, so that you can see the evolution more smoothly. When I sort of had time to think about this, having talked to Rafa, and sort of the night I couldn't sleep, I found when I actually thought about it, I was more interested in the question of how we mitigate systematic errors in the input data, which are not really taken account of in the inversion formalism. But I mentioned that to somebody and they said, this is a solved problem. So, but I think it may be worth thinking about. Okay, I think that's all I have to say. Thank you.
So anyone want to comment about how to solve these problems? It's your time to talk. Don't be shy. Please. Shravan is not here. But you're here, Sarvani. You have the mic.
Okay. So I agree with Rachel that understanding the systematic errors is very, very important, particularly given that some inversion methods like OLA and Solar are much more sensitive to systematics and outliers than something like the regularized problems. So in terms of understanding the data, I think that's very, very important. I rather like the idea of a 3D inversion where the third dimension is time, but like Rachel said, I don't know how to go about doing it. The other thing I think we need to do is figure out how do we do an inversion, yet not, can we do a sort of over-resolution where we have sharp edges, just like, you know, the tachocline. So I remember Frank Piper, I had a discussion with Frank Piper's, oh, this is more than 20 years ago when I was a postdoc in Aarhus, and Frank was there too. And he had said, he and Mike had discussed the fact that you could form custom target kernels, which would be sensitive to things like the first derivative rather than the underlying quantity. And I've never really tried it, but maybe that's something which will tell us about jumps and stuff.
On the same track but slightly different, you produce, Rachel, Sabani, all you guys are doing versions, absolutely beautiful pictures. But I sometimes think that actually extracting the meaning out of them is something we need to think about, how we go from these lovely 3D, time, and all the rest, but so that it's not a subjective response to it, but actually a quantitative response. And maybe that is a machine learning problem, to try and think what the machine thinks about. I don't know, but that would be one thing that I would say we need to think about.
I'd like to respectfully disagree with what was said. I have issues about, trying to over-resolve inversions, because the inversion is really telling us what resolution you have in the data, and trying to do ad hoc. We've done, I think with Phil Goody and Jambowski, we tried to add a discontinuity at the base of the convection zone. Just say, but that's essentially injecting an a priori assumption that there is a discontinuity. The real approach is to say, what are the data telling us about what's happening at the base of the convection zone? Which brings to the fact that, can we improve the data that we're inverting? We still are very parochial. Gong continue to do 108 days. Stanford insists on doing 72. So we cannot compare apple to oranges because we don't even have the same, time base. But, well, it is a head reading, but in some way, one way to look for systematics is to say, if two independent data sets that look at the same thing and analyze differently, don't give us the same answer, then we know that the difference is a systematic error. And then we can say, what is that magnitude of systematic error propagate to some inversion types, give us systematic wrong answers. And then we can go back to the drawing. But simply saying we're going to essentially sweep it under the rug by smoothing over time, the sun doesn't know whether time is smooth or not. So again, let's not inject or a priori assumption into the solution we're trying to invert. Otherwise, we may as well just go and give it to a 3-year-old and say, draw us what's inside the sun. And why is that not right? Of course, I'm a little bit, facetious here.
So I agree with you when it comes to the term over-resolution. What I really meant is get the gradients directly from the data without having to first get the underlying function and then try a numerical derivative or whatever you do. Because I visualize that as over-resolution because I can get the slope. Hopefully the true slope underneath. Probably, but still it'll be a better slope than taking 3 discrete resolution kernels and getting the slope from there.
Okay, but in that case, oh, okay, just.
I'm going to respectfully disagree with Sylvain's respectful disagreement. I mean, there's fundamentally no way to do an inversion without making a priori assumptions about what you're looking at. So I think complaining about that it's a bit spurious. there's much bigger problems in the fact that we are assuming that we know where the modes penetrate. We make that assumption from the models we use. And in terms of doing things like better resolving the base of the convection zone, I don't think we're going to do all that much better in terms of the data because the modes are there. I mean, we can get the errors down. Certainly there are systematic issues. But if we want to do better, I think we have to figure out clever ways of using the data.
Clever ways to produce the data. So, Sylvain, you were saying about data. So how do you improve it?
I'm not sure I have the answer to that, but one aspect that I found frustrating is that there is very little effort about both getting better models. I've said earlier, I would like to see to go away from just the adiabatic model so that we actually try to model what's happening close to the surface. I've put some effort to try to go to high L, which is very difficult, but if on top of that there's really no way of knowing what is happening close to the surface because nobody is doing the modeling there. And I think that this also, in some way, is not surprising that we have, even in local helioseismology, which is close to the surface, some results, people disagree about the sign of the signal because there is no guidance about what to expect. So it's all sort of related to the fact that, we cannot just simply turning the same crank we've been doing for the last, decade and say by just turning the same crank and getting more data that have the same systematics, we'll learn more.
Well, it's sort of a long-term discussion, and I may be digressing a little, but when we do these inversions, we always have a trade-off issue, of course, and so we need to choose, and that's part of the prejudice, because the trade-off that we do is based on that prejudice. For instance, in the ILS, that we want to make sure the solution is reasonably smooth. We have no guarantee that the sun is really smooth, and it could be oscillating like crazy. But in the ILS inversion, we suppress the second derivative of the solution, and which is probably fine, but we don't know. And so the point really is that what we are doing in all these inversion techniques, and we could go beyond that, that is not up there yet, but we're doing linear analysis on the data, and so we're just combining the data with coefficients, choosing the coefficients to get what we want to study, and we can do that in different ways, and we get different answers, and we get different insights in what we learn about the, in this case, rotation of the solar interior. And these different insights we then have to somehow combine into an understanding, if you like, of what's going on at the base of the convection zone or in the core and so on. And in some sense, if we trust the data and trust that there are no systematic errors in the data, we know exactly what we're doing because and assume that we know what the errors are and the statistics of the errors are in the data. We know exactly what we're doing because we have these coefficients, we combine the data using these coefficients, and so we can calculate error incurrence, we can calculate errors, and we can calculate error correlations between the solution at different points, which is something that we sometimes forget. And there we also very often forget that there might be error correlations between the data points that enter into the analysis. So in that sense, it's a bit of an art what we're doing. I mean, it's not, of course we want to call it science, but we have to use our intuition and to make the best possible use of all those wonderful data.
Yeah, I just want to make a couple of random comments also. The issue of the resolution, of course, in principle, you can say, well, what do you need for better resolution? You need higher frequency modes, which is sort of similar to the ridge fitting issue, that in principle, if you want better resolution, you need a shorter wavelength. But there was the other comment about the adiabatic calculations, right? I think saying that nobody works on it, well, of course, I have posted 28, and I'm sure that Rainer Tamberlach, who posted 29, would also disagree with that. And there are people doing analytical stuff, Günter Hudek, there's papers by Sonoy and so forth. So it's not that nothing is being done. It is let's say, a toxic problem. I mean, it is really unpleasant. I don't know when Jörn drew up his black box, he was referring to my black box on the poster, right? Because that is, you can say, oh, there's a black box calculation of the surface term. But trust me, we are trying to figure out some of the physics in it. But it is a difficult problem, but people are working on it. When we're done, that's a different matter. And actually, a bunch of the work was done the old-fashioned way with, a pen and paper and so forth to do differential equations and so forth. But I had to let somebody younger do that instead of somebody older, so I let Aaron do it.
And yes, we are some that actually deal with the atmosphere and try to model realistically. So we would urge the rest of you to use our results, maybe.
So then what do you need to improve even further your calculation at the surface and solve this bloody surface effects problem, which is close to be solved maybe?
Time. So I think I have it all right. I just need to perform the calculation to find out how to extract the surface effect from the simulations. So I have the structural part fairly much down, I think, and it's ready to get implemented in stellar structure calculation, so that it's part of the forward modeling of the stellar structure. And then the slightly more tricky part is non-adiabatic mode convection interactions that have to be incorporated into a non-adiabatic oscillation code. Still working on that.
Yeah, so I'd just like to change the subject a little and just address the issue of AI with machine learning issues. So the machine learning is only a black box because we haven't gotten in there and understood it, okay? Deep learning is a pompous name, but it has a very specific meaning in how the neural network has been set up. So these machine learning algorithms are really just highly nonlinear mappings from an input signal to an output signal. And you can adjust that mapping to inform what you're doing, just like any other mathematical technique. So I think we shouldn't be afraid of them. In fact, we should harness the power of these techniques and the underlying mathematics and learn from them and make sure they are run in the service of physics and our intuition of the physics. And I think there are people doing that, and there are ways of doing that. They're not the same ways that people use Google data to identify cats and dogs and make the Mona Lisa talk, but they are tools just like any other mathematical tool that we can harness to gain insight into the problems we're trying to solve. And in particular, there are problems that we cannot solve through typical analysis of PDEs and mathematical techniques that we're all know and love, and that require us to adopt these techniques to solve problems that have proven not solvable by other techniques. So I'll get off my soapbox.
Well, thanks for exactly doing what I'd hoped somebody would do, to comment on that. And I have some comments also on surface term, but let me just answer briefly to you. I agree completely that these are tools, and one could go back and say that when pocket calculators were introduced in schools, dinosaurs then lamented that the kids didn't learn how to calculate with numbers. So, and it's kind of the same thing that's happening now at a higher level. Tools are great, but you have to know how to use them. A chainsaw is a very useful tool, but it's pretty dangerous if you don't know what you're doing. You lose an arm. And similarly, these tools are wonderful if you know how to use them and how to interpret the results that come out. But if you just give it to somebody who has no idea what he's doing, then the results that come out are probably meaningless. So that's the kind of balance we have to find in applying these new tools. Same applies to symbolic algebra. That's wonderful, but it helps to understand what goes on in the analysis. And actually, I have a question for you concerning the surface term, because you defined a major paradigm shift in our understanding of convection, which is wonderful. But we hope we can still trust what Rainer is doing in terms of modeling these surface layers, which is where the surface effect on the frequencies come from, because if not, then we're dead. Then we can't really use what Rainer is doing, and which is our hope to understand what's going on in the surface effects on the oscillations. So, do you have any comment on that?
Yeah, so what I showed yesterday, I think we can get the mean thermodynamic state of the atmosphere. I don't know how to measure the filling factor and entropy fluctuations of granules on another star, okay? But with that input, we could get the thermodynamic stratification of the upper superadiabatic layer, which extends some tens of megameters. So that piece I think we could actually do theoretically. In terms of then using so we could do that maybe even without 3D models if we could make such measurements. Then the question about using 3D models, the 3D models are quite good in the surface layers because where they go wrong is in fact in the deeper layers where thermal diffusion has re-stratified the domain. So the reason one is so successful in using the filling factor and granules to be able to reproduce the upper superadiabatic layer is because largely the models have gotten to a point where there's very little diffusion over those time scales of the plumes descending through that layer. So I think we're safe in terms of what, if the large-scale motions that we're spuriously generating in the deeper layers aren't influencing tremendously what we see in the shallow layers, and there I would say run a shallow simulation so that you ensure that you're not driving spurious deep modes, then we can use those shallow simulations to understand the surface term. Okay. That's how.
Thank you. That's what I need.
Daniel.
So I want to go briefly back to the black box discussion. The second part of the black box discussion that Jörn showed, one was on the deep learning, and the other one was on what in the black box it was MESA. And so the reason why MESA is such a popular tool to use in the community is because it's open source. And so one of the things that I think as a community we need to think about, at least in the astroseismology community, is to produce more open source codes. So we recently had a workshop at KITP Santa Barbara where we brought together the stellar astrophysics, or the astroseismology community, and the exoplanet community. And we sort of compared, as part of this, an exercise, we compared the amount of open source tools that are out there for the community to use from the astroseismology side and the exoplanet side. And we're really lagging behind in terms of making codes available. And it's getting better. And I agree with Jörn that it's not an excuse to use a code without actually understanding what it does. But there is value in, not reinventing the wheel of some things that we know how to do, and everyone has to sort of write their own codes on how to do it. So astroseismic analysis pipelines, historically, we haven't been really good at documenting it, putting it out there for the community to use, including someone who works on exoplanets and just wants to analyze a star without having to run to an astroseismologist. So I think that's something that we're getting better as a community, but I think there's still some way to go. And that's one part of the black box discussion, I think that's actually sort of valuable to think about.
Let me turn to a different little theme, partly fired off by Mark yesterday morning. And one of the distinguishing features, I would say, of solar physics as opposed to stellar physics in our helioseismology versus asteroseismology is that we've come quite a bit to the point of understanding where some of our problems are. And I would say that the problems are, we have two boundary layers in this star. We have a near surface layer, which is really distinguished, well resolved, and we don't understand how it comes about. We have not succeeded in any of the big models of one sort or another getting it in a natural fashion. And the other issue is we have a tachocline, which does something. Gene Parker and others said that the dynamo must operate there, and flux transport models say it's all about meridional circulation. We haul it down to the bottom, and dynamos will operate. Well, things have happened, at least in the last 15 years or so, which show that the highly turbulent convection zone can actually build large-scale magnetic structures. They may not get the cycles in a way that we're comfortable, but the heliocosmology has allowed us to show some of the things we know and also things we do not know. And I hope that in the continuing efforts in this subject, we continue to confront these issues, and remarkably, a star like the Sun, simplest one, at least we know, at least we see in detail, has these boundary layers. Aviation depends entirely upon boundary layers. When an airplane stalls, it's because a 1 or 2 millimeter thick layer has separated. We don't know how these boundary layers come about and what they do. And Mark very nicely showed yesterday that this delicate issue of how adiabatic minus del add some sort of, which is some very small number, how it may make a difference between the types of motions that are driven. We have a lot of work to do in basically the sort of fundamentals of fluid dynamics that bear upon the Sun, and the Sun is a great resource. But I hope that some of the things we did to put together a picture from heliocosmology of how the differential rotation functions in the Sun with 2 boundary layers, that we actually somehow make headway on those boundary layers. The upper boundary layer may be your surface effect, but it's also perhaps dynamically extremely important. The computers you showed us, they help provide us thinking tools. I mean, most of us are basically in the Gedanken by numerical methods, trying to understand what they may yield. And I'm sure that is the direction in which quite a few of the astrophysical fluid dynamics will go, because they're highly delicate and very nonlinear systems. So I applaud the talk by Mark pointing out the inconsistencies that we need to be looking at on a very regular basis to figure out what do we understand, where are the problems, and I would say for the Sun, it's 2 boundary layers, which we really we do not know the responsibilities that these boundary layers have, or how we, in a self-consistent fashion, really get them.
So I'm going to first address an issue raised by Yuri and then go back to Dan's comment. So you talked about the boundary layers, and of course things are, other stars are showing that things can be much more complicated, because now we know of existence of stellar activity cycles in stars that are completely convective. So now that's an interesting problem by itself, I think. So yeah, boundary layers are important, and the question is, if boundary layers are tantamount, why are the lack of boundary layers also giving a similar phenomenon? Now, to go back to Daniel's comment, just because a code is open source doesn't mean people are not going to use them like a black box. And I'm getting quite tired of people making models with MESA which are completely and utterly wrong. So what? Again, exactly. And the utility. No, you can fix it only if you know where the physics is going wrong, that you're using wrong parameters. People keep saying MESA doesn't have free parameters, which is complete and utter nonsense. Its in-lists are huge, where you actually have to put in the parameters needed to model a particular star.
Can I follow up on your point? Because
Yeah.
I totally agree with you. You made an interesting, almost an aside, Dan, which talked about support. If you look at a good open source or not package, I use ones in IDL that are just provided, they come with more explanation than actual coding. And one of the things, and I'm totally with Sabani in this, is good open source is brilliant, but are you actually going to put the resource in, the personal resource in, to support the people who are using your code, and to be sure that it works in all the crazy circumstances that they choose? So you've got to put in all the ifs and buts. If you write commercial software, you spend a huge amount of time dealing with the stupid things people are going to do with it.
Yeah, I agree that that's necessary if you make your code public to actually have, I mean, I said that you have to have documentation and people guide the people in the right way to use it. But the other important thing which reflects what Sabani said is that's also a tool for the community to actually get engaged. It's not just one single person having to write a code and putting it out there and then there's 1,000 people using it and sending you 1,000 emails when they use it. They can contribute to the code as well, right? And that's what happened with Mesa. So there's a community that builds those tools and that makes them better. And so if you run a Mesa model and it comes out and it's completely unphysical, it doesn't show what it should, then the code is there and we can fix it because it's open source and people can look into it. For codes that are closed, that's more difficult to do, and to reproduce the results and how they are, you essentially have to have access to the code to get behind it. So
Yeah,
understand the...
But we've been doing that anyway, and no, and your other statement that why duplicate efforts, it's, to me, a code is an instrument, and just like two different instruments can give you two different results for the same observation, one of the big things like Jan has been leading is comparing the results of stellar evolution codes. Do you get the same thing when you input the same thing? So, and without that comparison, you don't always know that you're getting nonsense.
No, I agree that we have to make those comparisons, but those comparisons would be much easier if all the codes would be publicly available. So I don't want to be like the defender of Mesa. I don't develop Mesa, but I'm just advocating.
So there, I think
We move forward.
there are actually two different issues being discussed here. I think you guys are kind of talking across each other. One is how you use codes that you have, and the other is how do we develop codes for the community. You're talking about good practices in community coding, and Sarbani is talking about understanding the codes that you use, whether you've written them or somebody else has. And I think those are two distinct issues. As a community, I think we really should be thinking a lot more carefully about how we provide code to other people, how we document it, how we validate it. But then there's the flip side, which Sarbani is talking about, which is basically just garbage in, garbage out.
Probably when these codes can be used, the boundaries on the use of the codes. Jesper?
Yeah, it's maybe just repeating what's said, but I just remember, I'm not a user of Mesa, maybe I should be, but I remember a few years ago working with someone who shall remain nameless, who kept producing a lot of very interesting results. And every time you see these results, you go like, hang on a second, that's extraordinary, that is really strange, you know, and you find out, oh, it's because some parameter isn't set right. Same thing in oscillation codes, same problem. This being open source is all nice and good, and I strongly support the general concept, right? But people do use them as black boxes. Right? The fact is, people use these codes as black boxes, and the criticism of what you see, which I think was what Jørgen said earlier, right, is like, does this make any sense? And the stuff comes out, you can say, well, it's reproducible, that's all very nice. But in the meantime, you've polluted the literature with a huge number of weird things and wasted people's time. Yes, you can break your leg again and again and again. Actually, you can't. It turns that there's a problem with breaking your leg twice the same place. But apart from that, but it is really it's used as a black box, right? And people make these mistakes. And I'm not saying it's easy, because that's actually often an argument that comes around about open source code. That's sort of, I think, so two really big problems, right? One is people come running and saying, oh, this closed code you're using, why don't you just make it open source? Well, because it's against the law. Okay? Yes, it is. Because a lot of these legacy codes have procedures that are written by other people over decades. It is a violation of copyright to actually make that open source. Okay? It is against the law to do so. You have to rewrite it. Okay? That is a fact of law. This is how it is. And the other one is this thing about support. You go like, oh, I'm going to make this code. You can just make your code available. Sure, I make it available to you. Okay, 1,000 people use it. I have nothing else to do in my life than answering questions about people who can't. And then the people go like, oh, you might better have documentation. Look, sorry, we don't have the resources to necessarily do that for that code that's 20-year-old legacy code. It just doesn't, you know, yes, the funding agencies maybe go up, apply for a grant and get a lot of money to do. These are non-trivial issues.
So a historical note, a few hundred years ago when Galileo and other scientists would derive equations, they would keep them in a sealed envelope for decades until they were rederived by another scientist. And then they would unseal them and say, I did this first. This is the situation we have today with source code. And I think it's not a good practice for science. I don't think it's good that we hide away our algorithms. There's no distinction between an equation and an algorithm. Mathematically, they are equivalent. And so we should share our results. Now, if you put out an equation and someone puts in the wrong numbers in that, we can all agree that's a bad thing to do. People are doing that with source code. Yes, they shouldn't be doing that. But that's no argument against open source.
Yeah, I was going to say the same thing. I don't know why we're really talking about whether somebody uses a code in a lousy way or not, because no matter what tool you hand to somebody, somebody will going to use it well, and people are going to use it crappily, and so that's why we have peer review. So I just had to add one thing to the service term discussion, Jan. I think one of the most important things we've learned is that the sun, the surface of the sun, the granulation that we can model well, is essentially magnetized, which means that we have to understand the surface term in the presence of magnetism and in the presence of varying degrees of magnetism, and I think that's a real challenge for the future and one that we should rise to the challenge for.
I think that we should move on. I just want, because I'm the chair, so I have the right to add something to the discussion, which is just, it's a matter of common sense. I mean, if someone uses an equation in the wrong boundaries, it's wrong. If someone uses a code with the wrong parameters, it's wrong. But it's a matter of us as a community to teach also the new generations. You are completely right, but I can't do it. I'm the chair. So, yeah. So, okay, so we move on. Yeah, I always forget that I have already one. So I was saying, no, it's already one. So, okay. So just moving on. And to the modeling now, because we have talked a lot of things there. John is telling me something. Okay.
Just a quick comment before you go on to modeling, to reiterate the importance of Rachel's comment about taking the time domain into account. We started off with just a series of snapshots, and we did that because computing resources were limited, and quite frankly, we didn't know what we were doing. And that legacy has lasted far too long. It's really antiquity, and we really should be thinking in 3 dimensions, whether it's inversions or just the simple analysis of time sequences of images. It's a really important point not to be lost.
Okay. So I want to move on modeling. So we have our beautiful stellar evolution codes. We have MJT codes. I don't know if I am listening. So I would like to have the idea of the views of the expert here. So Sasha, just it's you. So you have a wonderful project, the whole sun. And I want to know what should be the next, which is the whole star. I want a structure and evolution code coupled with ASH at all stages. So is it possible in 20 years' time, 30 years' time, 100 years?
Well, I think I already answered a little bit that question during my talk. I think right now we are certainly having effort to develop 2D stellar evolution code. 3D stellar evolution code, they were an effort by Livermore and Peter Eggleton and Sylvain Turcotte many years ago. I'm not really sure what this went to in terms of, I haven't seen Sylvain for many years. Peter, I haven't bumped into him, so I'm not really sure what this effort in Livermore ended up to. So there were already some attempts to do a 3D stellar evolution code. This is extremely difficult, as you know. So I think what we have been doing recently with a PhD student was to model the PMS, the Primary Sequence phase of one solar mass star. And we use the 1D model to pave with 3D simulation the evolution and look at what happened to the field when the convective envelope is receding as the star evolves through the PMS. So that was very interesting, and for instance, one of the key results of this work was to show that the magnetic field left through the dynamo action in the PMS phase is actually Taylor stable. So the mixture between poloidal and toroidal field left by the receding core is stably stable. So I'm not expecting the sun to have a purely dipolar field. It's likely if he has a primordial field to be stable and a mixed polarity. But that being said, to directly answer your question, I do believe that 2D evolutionary code can be done. Michel Riotor is developing the code Esther that can take into account deformation by force, centrifugal forcing, so when you are really rotating fast. And I think there have been attempts to look at aspects of that. For example, I know Nucio Lanza, Günther Rüdiger have done some kind of spin-down models of 2D simulations. So yes, I think clearly in 10 years or so, we should have a 2D evolution code. 3D, much longer, I think, still.
Okay. So then, thank you, Sasha. So anyone want to comment on that? Coming ready.
So we've had 2D and 3D codes before, and correct me if I'm wrong, I thought Peter Eggleton's 3D code was a stellar structure code and not a stellar evolution code. They evolved it to a point and then took tiny time steps to see what the 3D nature would do. And similarly, Bob Dupre had a 2D code to see the effects of rotation, and that too wasn't an evolution code, it was a structure code. So I suppose the question would be, can we do evolution and structure? I mean, it's done in 1.3D these days. The Geneva code is essentially a 1.3D code in some sense. The Yale rotating code so is, but can we really do structure and evolution?
Yes, I think you can do it. Your point about convection is important in the sense that convection is fundamentally 3D. So is 2D convection a better representation than MLT? That will need to be looked at in detail, certainly. But yes, I don't see any technical difficulty. I see a lack of manpower or woman power in working in trying to develop such a code. So.
So 2 points. One is, I always thought, I may be wrong, maybe there are better ways to do it now. The problem about doing convection at the same time of stellar evolution was a time-stepping problem. And the second comment / question is that we know 2D simulations of convection have been quite different from 3D simulations of convection. So your comment about 2D simulations, 2D convection.
Yes, no, Sabani, you're totally right. I think how many of the current 1D stellar evolution code are fully parallel? So I think many of the stellar evolution code nowadays are at best running on a few core, maybe. So I think that if you want to do 2D stellar evolution code, you have to develop a code that will be MPI, that will be, you will be able to run on thousands of core to solve that problem. And also there are some new techniques in time integration that are called parallel in time techniques that can, we are very on the edge in terms of time stepping, for instance, that we are doing still a finite difference. Or that for the space resolution, we have finite element, finite volume, a spectral difference method, and et cetera, and spectral methods. Nothing has really been done to implement spectral method in time. And the parallel in time methods are to apply spectral approach to the time stepping. And so we know this has potentially some difficulty, but we know it works. So we could definitely develop a new 2D stellar evolution code that is parallel, that has modern technology in terms of time stepping, in order to be able to go to a long time scale and deal with the short time scale with a predictor-corrector approach. So there are ways. I'm just saying we are lacking the man and woman power to actually have serious people who develop code to learn from the Lagrangian 1D code and to expand it to 2D. There are ways, but is there the effort? That's less clear.
Okay, thank you. We have to move forward. So now we move to observations. So I have a few comments there, if someone wants to say something. So if we want to move forward, we'd like to, as usually, Jesper, Sylvain, but also the other ones, do you want higher degree modes? You said before, Sylvain, that you wanted to go as much higher as you can to tackle the surface as much. I would also like low frequencies. Anyone have a comment on that? The last one, but probably we cannot do that. So, okay.
So it's again, we can compute something. The question is, how well can we compute it, and can we really believe it? And some of the primes go back to the fact that, we have poor tracking of some of the basic information we know about image orientation. It's very, very difficult to pull high degree modes, for a lot of different reasons. And while yes, and at low frequency, we're hitting a signal to noise ratio. So yes, we can try to measure something, but what's the significance of it? And at the end, we measure something with the huge error bars. Do we really get more information?
So, Jesper?
Well, I'm reading a little bit ahead and a little bit on that subject there. I mean, actually, one of the things I've sort of wondered about is, people say, oh, multicolors, different heights in a line and that kind of stuff. And I'm kind of wondering, it would be really nice for somebody to do a calculation that shows whether it can be done. Really. I mean, and you can say, well, I don't do it myself. Well, I mean, I'm pretty lazy. So, but it would just be nice to actually see, can that be done? One of the other questions we keep kicking around, can you beat the Dirac limit? Either by saying something about modeling the source based on what's here on the surface, or by solving for some kind. See, the Dirac limit is one that basically says, which actually really doesn't belong to Dirac, that's an older one, that basically says that the Ionosphere mode frequency is basically limited by the square root of the line width over the time that you observe it. And I think it would be wonderful actually to just understand these two questions, can it actually be done? And I think that some of these questions are probably within what could be answered, either numerically or by some really clever person. But I think that would be interesting.
We hope to have
the stellar imager sounds great.
Yeah, so we hope to have your answer in the next meeting. Thank you, Jesper. So if we move forward again for instrumentation, so Dan showed this morning that we will have a bunch of asteroseismic detections, etc. So that's great. But seismology alone can probably not do as good as coupled to spectroscopy. So you showed the figure with W first and with Plato, etc. How do we do the follow-up? We need spectroscopy. So
yes, that's a challenge. Of course, the answer is multi-object spectroscopy, which there's an era now where a lot of instrumentation is built, and there's future projects like MSE on the Mauna Kea Spectroscopic Explorer. That's a concept for expanding one of the existing telescopes and make them a multi-object spectrograph. But apart from just getting the spectra itself, I think another important thing is to actually understand the parameters that we get out from the spectra, and that goes to improving our understanding of the model atmospheres that we use to extract things like effective temperatures, metallicities, chemical abundances. There are quite a few systematic differences when you do exercises such as, here's a spectrum given to different groups, derive these parameters. It's quite a similar level to the sort of exercises we do in astroseismology, and I think getting to the bottom of these issues is going to be really important so that these are not a bottleneck whenever we actually want to combine these data sets. And that actually goes into the more fundamental way of measuring properties of a star in complement to astroseismology, which is interferometry. The interferometry community, but it's incredibly important because the angular diameters are what really ties our temperature scales and our independent radii all together. And so I think there needs to be, it would be great to have more support from the global stellar community, including the astroseismology community, to these fundamental measurements. Resolving stellar surfaces, right? That would be great if we could actually, there's been papers, I think there was a Nature paper 2 years ago where we resolved granules on a red supergiant using interferometry by actually doing image reconstruction. It's not impossible to push this to much smaller stars, sequence stars, but of course it requires instrumentation, longer baselines, larger telescopes, and that requires funding to get there.
John?
There are two known unknowns that come immediately to mind, looking at maybe the first bullet and the second. The first is the core. We don't understand the core, I would say, at all. And lacking ingredient is G-modes. And we clearly need a major, sustained, observational as well as theoretical push to solve this far too long-standing conundrum. The other is the poles. We're looking forward to the opportunity with Orbiter to do stereoscopy, helioseismic stereoscopy. L5 offers the opportunity as well, and both of those need to be pushed. The helioseismic aspect of both of those need to be pushed very, very seriously.
Maybe if I am a little bit, if I push a little bit far, you want to go to the pole to see the sun, but we have thousands of poles in stars. So what can you do? Because this data is there. Sorry?
The issue is we can't resolve the poles of other stars. So if the solar pole is, say, for instance, as interesting as the Juno images of Jupiter with all those whirlpools, do we know that? Where does the meridional flow actually flow down?
Well, we know from the background measurements that there is no clear differences, so at least in average, there is exactly the same in stars.
I'd like to pick up on Dan's comments about improving our interpretation of classic observations. I mean, every time you do an astroseismic fit to figure out what star you're actually looking at, you need also the constraint from classic observables. And usually there is a tension between the two sets of observations, which means there's something we're getting wrong. And you're pointing out how how spectroscopy and abundance analysis is highly degenerate, with different teams getting wildly discrepant results at times. So one project I hope I'll be able to work on soon is to develop averages of 3D surface simulations that can be used for reliable reconstruction of synthetic spectra that are much cheaper to perform than full 3D analysis, but will give the exact same results. So you can actually do 3D spectroscopy for fairly cheap. So I hope that will help on that situation. And of course, there'll also be limb darkening for those same simulations for the interferometry.
Okay, so John?
Just a comment to John's comment about the core and the pole. With rotation, yes, we don't know anything about the rotation of the core, and then that's a big problem. For the structure, I think we have to remember that neutrinos are back in the game as diagnostics of the core structure of the core of the sun, because we now understand the neutrino oscillations well enough to use those data in a sensible way. On the pole, my feeling is we have a little bit from Hinode and the polar structure, just from very skewed observations of the pole. But of course, we hope that we are finally going to get Solar Orbiter launched. And then in a decade, maybe we'll have a view at a slightly better angle of the pole, and we'll begin to learn something about the properties of the solar pole. So there's hope.
Okay, so moving to the instrumentation part, just Laurent, John, and myself, we went with Michael 2 years ago to Abu Dhabi to have a discussion about the future instrumentation on the sun. So don't be ashamed. So I wanted John to tell us what he thinks about what should be the next generation of spacecraft that you would like after what we have said here for the sun or for the stars.
G modes, G modes, G modes.
I will add G modes, but in all HR diagram in the main sequence, not only in the sun. So, Jorn, 2008, HILAS, Lanzarote, something like that. You talk about the stellar imager. So, I think we want all the stellar imager.
Well, the stellar imager has been in the cards for a long time to have a flotilla of telescopes resolving the structure of main sequence stars in photometry. There's been a lot of talk about doing that in the UV because one of the issues was to resolve activity properties of the stellar surface. But I mean, technically, I think it's could be feasible. What we would be able to do there would be astroseismology at degrees, I think the resolution would allow up to a degree of 60. And so we would be able to see the tachocline if we could measure the rotation, resolve the internal rotation in these stars. And again, I think there's nothing stopping us from doing that from a technological point of view. I mean, if we can do LISA, we can control satellites, information flying very accurately. So it's just a matter of money.
So, Marcus?
Yeah, for the sun, if we go away from the ground, my preference for the ground, you know. If we go to space, I would say we want a multi-vantage point mission. Linking back to your first slide is leakage. We want to get rid of leakage. That means we want to see the full sun, the backside, the side views. We want to reduce leakage. That would give us meridional flow measurements down to the base of the convection zone and deeper. That might help us to detect the G modes, linking to John's suggestion. So if we do something in space, I would say we need multi-vantage point views on the sun.
Okay, thank you. So any other comments on instrumentation or something like that? Okay, yeah.
I think one other thing we should be thinking about is how we're going to get very long baseline helioseismic measurements, and it's really hard to justify a replacement for something like HMI, given that there's not, unless we talk about multi-height, there's not a whole lot to do. So one thing that I would like to push for, and I don't know who to talk to or who to prod, is turning it into an operational capability, sticking a little MDI-like on a GOES satellite. That obviously gets it kind of outside of our control, because then NOAA or whoever takes it over. But I think it would be a real shame if we, 3 or 4 decades out, we have a big gap in our high-resolution helioseismic observations.
So I will just add that probably Yvonne will agree with me that we want a Kepler running again with 20 reaction wheels and being in the same field for the next 25 years, right? Okay, so just moving for the last part. Comments about what we haven't yet learned from the stars to apply to the sun, because we have many suns out there. Not with the same resolution, agreed. So, anyone want to comment about that? One thing is the poles, as I said. And we know the general background properties are the same. We don't see very differences. Dynamos, we have dynamos in many stars. So I think it's something that should be explored by the solar community, not only by the stellar community or the people that went to the dark side following Jorn. But yeah, I think that's something that's important, and we should do that. So if there are no more comments, I want to make a final question. Oh, sorry, Jorn. Robin, I told you already I was going to do that. So, yeah. How can you apply inversion techniques to tell us more about epidemiology and...
That's a good question. So initially I'm going to ignore the question and just say that a lot of the issues that have been discussed, particularly the ones at the beginning about using open source code as a kind of black box, those kinds of issues are very, very common to lots and lots of disciplines, of course. So if anyone here finds a solution, then please share it with everyone else. In terms of inversion methods in epidemiology, I guess obviously I'm not sure. However, I guess some of the underlying questions in some of the stuff that's been presented this week clearly applies for infectious disease outbreak modeling. So questions like, if you have very, very kind of messy data, how can you separate that back into the kind of individual kind of things that make up that messy data? That's a very, very important question. So for example, you might, what you want to find is you want to find out the dynamics of a particular infectious disease. So you might want to understand the time series of Ebola, for example. What you see in your data is not that. So what you see in your data is a time series of symptoms, and you have absolutely no idea whether those symptoms, those hemorrhagic symptoms, are because of Ebola or because of any other number of possible infectious disease outbreaks. So really, it's multiple time series all added together to come up with one time series of symptoms. And so being able to kind of go backwards and unpick that time series into the underlying time series would be something that would be very, very useful. And so I guess one way, so the kind of forward model, backward model idea that a few people have discussed would be really, really great. Because I guess we understand the dynamics of Ebola quite well, but what we don't know how to do is to go from time series of symptoms for lots of things back to individual time series. That might be one example. I'm not sure. I don't know if anyone else has any other ideas. It'd be cool to hear.
Okay, I think that you have 40 years to solve the problem, but we were looking forward to see it. Looking forward to see it. The discussion, that it went very well, I think. So let's give the talk to.
Congratulations, you survived. I barely survived. In fact, my phone is still on a telecon in the back of the room. I don't think they know that I'm not listening anymore. Shows my participation, right? So I have 332 slides to get through. If anybody's got a flight sometime before tomorrow, I would suggest you leave now. Anyway, so just wanted to wrap up. And I think that the conversation that you just had is a start of a conversation and a bigger conversation that needs to continue. And I think, in the preparation of this meeting, and certainly I remember, a year ago talking with Michael, the sense was that these meetings didn't happen frequently enough. And he was concerned that the momentum in the field had been kind of lost as a result of not having enough community interactions. And so, my first step in closing here is I'm going to challenge you all to keep thinking big. Over the next day, there are a few splinter sessions, and I know they're focused largely on the sun. But I encourage you all, if you're around, to participate in those splinters and give the benefit of your wisdom to those splinter groups to set up requirements for next generation hardware to it's just to characterize our star, but who knows what those techniques, what fruit they'll bear in the broader astro-seismological world. But keep developing those challenging goals. When Michael and I were conceiving this workshop, our focus was on the future and trying to deal with, what appears to be an impasse in the field. How can we help? How could HAO contribute, even as a hub, to bring people in and encourage this interaction on a more regular cadence to see if we could break some progress through? And so I would challenge you all, and look at my colleagues on the SOC. Can the SOC stand up if they're still in the room? Or is it most of the room? I want to thank you all on behalf of myself, the staff of HAO and NCAR, and Robin and Kate, of course. For putting together a very, very thoughtful set of presentations to reflect on someone who we all consider as being a glue-on, someone who was a thread that bore through. There's at least 3 different types of communities in this room. Someone that had equal impact in each. And I think that that's a very strong thing to say, even beyond the fact of what a tremendous mentor and leader and administrator that Michael also was, that some of us had other experiences with. So I think this he would have liked. But I know that he would have appreciated a follow-up on this and for this to continue. And so my charge to the SOC is to find a time, sometime in the not too distant future, to come back here and aggressively go after the things that were discussed in that last 40 minutes. And let's look at how those come forward as a community and then progress. Now, Steve, thank you very much. As the chair of the LOC, you've done an amazing job, and I will bribe you with many beers over the next coming weeks to thank you. And finally, in rounding up, there's 2 people, I believe, that without whom this meeting wouldn't have been possible because they carried a tremendous load. The first would be Cheryl, who's hanging around outside the room, and I know she doesn't like flowers, and she really doesn't like praise. And so I don't have flowers, but I'm going to heap praise on her. Because Cheryl is a pretty formidable person. She's kept this whole meeting on track. She's basically taken the brunt of my crazy schedule and transposed it and kept everyone else in phase. So we're all phase locked. And it's all thanks to Cheryl. Thank you, Cheryl. I have a small gift for you. Yeah, thank you, Cheryl. And I won't tell them what that is, Cheryl. You can keep that to yourself. But let's just say she likes hard liquor. Okay? Okay. And then lastly, and this maybe is of most relevance to the entire community here, that JCD, thank you very much. I owe you a great debt for taking this on, and I think you've done a formidable job of representing the spirit of the occasion and bringing the science together, and I don't think it would have been possible without your considerable effort. And so, on behalf of everyone, I want to thank you, and I have a cheesy gift for you if you would like to come up. It's almost as an MJT-ism. I present you with I love Colorado. Thank you very much.
interaction, fun, good discussions, blowing the top of some of us from time to time. It's all part of it. So it's been, I think, really a very, very good few days. And you're right, maybe we should think about doing it again.
The facility is available. So that's the charge to the SOC, so remember that. You're on the hook for the next one too. So, again, as Jorn said, thank you all very much for attending. Again, I encourage you to participate in the splinters. Safe travels. Please be safe. Don't work too hard. Take my example. You're either working hard or hardly working. So, thank you very much, Kate and Robin. Thank you for your patience and participation over the week. I did learn a little bit about epidemiology this week, I guess. So thank you. And with that, I'd love to close the workshop. Thank you.